Remember checksumming from our discussions in the transport layer. In TCP and UDP in the transport layer, as well as IP version 4 in the network layer, we have a checksum field. These protocols use the internet checksum as defined in RFC 1071. For this checksum, for example, at the transport layer, at the sender side, bytes are paired to form 16-bit numbers, and the ones complement sum of these 16-bit numbers is calculated. In general, this could be done for any selected number of bits. To detect errors, the checksum over all fields is calculated at the receiver side and compared with the provided checksum in the segment. Remember from our same discussions in the transport layer, the scenarios we use to show the errors that could not be detected by checksum. For this reason, the weakness of the checksum mechanisms, a more complicated mechanism is required at the link layer. Cyclic redundancy check, or CRC, which is also known as polynomial codes, is a more powerful way of detecting errors. Using CRC, we view a bit string as a polynomial with coefficients of 0 and 1. Let's see how CRC works. Assume we have d bits of data, and we represent the contents of these d bits with capital D. Now, choose r+1 bits with the bit pattern or value g. We call it the generator. This value is decided between the sender and the receiver and is known to both of them. The leftmost bit or most significant bit of this generator needs to be 1. For d bits of data, the sender chooses r bits with value capital R that meets certain requirements and attaches them to the data bits. The requirements that these bits need to meet are that the values stored in data bits and these CRC bits put together that have the length d plus r should be divisible by the generator using modulo 2 arithmetic. The receiver knows the value of g, so when the receiver receives these r plus d bits, it divides them by g, and if the result is non-zero, it knows there is a problem. CRC mechanism can detect burst errors of up to r+1 bits. This means consecutive bits with length less than r+1. CRC can also detect any odd number of bit flips. This is a mechanism that is used in practice. For example, in Ethernet and 802.11 or Wi-Fi. The remaining question here would be, how does the sender compute the value R for the CRC bits to attach to the data bits? Modulo 2 arithmetic in CRC is performed without the carrying addition and without the borrowing subtraction. Therefore, the addition and subtraction are the same, and both are done through exclusive OR. Now, we are at the sender side, have d bits of data with value capital D, and we want to compute the value of CRC bits to attach them to the bits we want to send. Let's see how we find that. The value in d plus r bits is capital D times 2 to the power of r plus capital R. Because by attaching r bits to the right, we are multiplying capital D by 2 to the power of r, and with setting those bits to the value of capital R, we are adding it, which is identical to XORing it with the rightmost zeros. This whole value should be divisible by the generator, so it is equal to multiplication of some number n to g. That is equal to saying capital D times 2 to the power of r is equal to ng XOR r. Now, we do the division of shifted data values to g at the sender side, and since add and subtract are the same, adding the remainder to the initial value will make it divisible. This will be double-checked with the same arithmetic on the receiver side, knowing the g at both sides. Let's see an example. Say our agreed upon generator is 1001. Our data is 101110. Remember, g was r+1 bits, and G is 4 bits here. So the number of our CRC bits R is 3. So D times 2 to the power of 3 is just shifting our D 3 bits to the left. Then we performed division, step by step. And the final remainder value is the value of R we will use as our CRC bits. Here we have 6 bits of data and 3 bits of CRC. And our generator was a 4-bit generator at this example. There are international standards for 8, 12, 16, and 32-bit generators.